Anytime I ask somebody, are you comfortable? The first thing they usually say is, I'm not sure, let me go check the thermostat. We've got a lot to talk about, so like any presentation, it's always really hard to figure out how to whittle this thing down into a manageable amount of time, because there's a lot to talk about. So some of this I'm going to move through pretty quickly. We'll try to do questions at the end as much as possible. But let's start off with comfort, right? And so anytime I ask somebody, are you comfortable? The first thing they usually say is, I'm not sure, let me go check the thermostat. and the reality is we are beholden to this thermostat, to this thing on the wall. And people forget that there are 6 factors that actually affect thermal comfort in a building. It's not just the temperature. That's one, of course, air temperature being one, but there are 5 other factors. Does anybody know the other 5 factors of thermal comfort?
Convection.
Humidity. Relative humidity, that's 2.
Radiant surface temperature.
Air speed, that's 3, right? If I blow across your skin, I get evaporation, I get a cooling effect, right? So air speed, how much air velocity is going across your skin. That's number 3. Any others? Surface temperature, we're going to get there. Hold that thought. Yep. Radiant temperature, we're going to get there. Yeah, the surface temperature, radiant temperature, we'll talk about that in a second. Noise is part of the IEQ. Yep, acoustical noise, but not for thermal. Yep, but IEQ, definitely for sure. I'll keep going here. Metabolic rate. Am I running on a treadmill or am I sitting at a desk? Right, the activity level of the person that's in that space matters. Clothing, right? Nice work, Sarah, nice work. So clothing insulation matters, right? Am I got a woke sweater on and fully clothed, or am I literally in shorts and a t-shirt, right? That matters. The last one, which 2 people mentioned, radiant temperature and surface temperature, which is the same. It's called mean radiant temperature, and that's a function of I experience in this space an average of every surface around me. So basically the floor, the ceiling, that wall, this wall, and that wall. The average of all those is what my body feels. The best way I can describe mean radiant temperature is if I was basically on a cold winter day in the sun or in the shade. All these are the same except for that. My clothing level is the same, my metabolic rate's the same, my airspeed, the wind's the same, relative humidity, air temperature is the same. The only thing that changes is I have a nice object in the sky that's beaming infrared energy to my body to make me feel warmer. Right? So mean radiant temperature, and why you feel cold in front of a large window on a winter day is that glass is pulling heat from your body, right? And that's all a function of mean radiant temperature, okay? So comfort has 6 factors, and we want to blame the HVAC system on all of these, but it's not always the HVAC system's fault, all right? So hear me out. Here's an example. Someone's working at their desk at their house, it's 70 degrees, the thermostat is satisfied. Thermostat's good to go. But no, I got a hot wall there, I got a hot attic there, the mean radiant temperature is awful, I got a lot of infiltration, I got 70% relative humidity, I've got a problem, I've got an uncomfortable homeowner. So what do? They crank the thermostat down, 67, 66, 65 to try to get comfortable. It's the wrong way to do it. It's the wrong way to do it. But it's not a function of the HVAC, it's a bad enclosure in this example, okay? So people think that buildings are static. Yes, they're static and they don't move, but they're very dynamic in terms of the nature of how they operate. So you think about outdoor air temperatures changing, humidity is changing, solar gain changes, right? Wind, infiltration, mechanical ventilation, internal gains, door opening, stack effect. The building is dynamic, changes a lot, okay? So I'm gonna show you, I have a couple of technical slides. This is one, it's called the psychrometric chart, okay? So let me just explain this real quick. This is every condition that air could be at. If I move left, I'm colder. So in this example, that's minus 10. This is 120 degrees. So think about outdoor air temperature. Really cold over there, really hot over here. And then the y-axis is humidity. Really humid up here, really dry down here. 10% all the way to 100% humidity. Okay? HVAC systems need to keep us in the sweet spot. That's between 70 and 75, right? 70 to 75, and between 30% and 50% relative humidity. That's the 30% line, that's the 50%. I need, X marks the spot. I need to be in that zone, right? All the time. I also need to ventilate. I need to bring fresh air in. I need to do source capture for my kitchen, my bathroom. I need to filter that. The HVAC needs to do a lot, right? Now, if I overlay this perfect, warm, cozy spot in a house that I want to be at, with all of the temperatures that Boston sees, this is what you get. So these are all the bin hours that Boston operates at. Guess what? We're never at those temperatures. We're there less than 18 hours a year. Okay, so each blue dot is up to 18 hours. So think of it as a day. Each blue dot, think of it as a day. Red dots are like 5 days. So we spend most of the time in Boston right down here in this 25 to 45, maybe 50 degree temperatures in the low humidities, obviously because it's dry in the wintertime. Here's our heating set point. Here's our cooling set point. That's 70 degrees, 30% relative humidity, 75 degrees, 50% relative humidity. So we're never at the sweet spot, right? So the HVAC system, again, has to work hard. So what do? So the business that I run is called TE2 Engineering, and we do HVAC design. That's our kind of bread and butter. We do mechanical, electrical, plumbing, and fire protection design. But the HVAC design is a function of the residential or commercial standards, and we use the ACA standards as a baseline. They're not perfect, but they are a baseline, and they're code adopted in most jurisdictions. You might hear the word manual J. Does everyone know what a manual J is? It's called manual because it used to be a manual, like a book. You have to, when I first started, you'd go to the book and you'd fill out the tables in the book and do it the longhand way, right? Now it's done by software, but it's a manual J, and J stands for joules. That's energy transfer, okay? Manual J. Then there's manual S, which is the equipment selection, right? If I have a load, I need to pick equipment to meet that load, and it's gonna have to be a little bit bigger than that load in many cases. Then I have to do if it's got ductwork, I gotta do a ductwork design. That's manual D for ductwork, right? And then I have air distribution, manual T. That's the registers, the air that blows out through the supply, and the register on the return that brings it in. That's manual T, okay? There's other calculations that we do, which is ventilation, right? Getting the ventilation right. How much outdoor air do I need? How much exhaust air do I need in a building? And the humidification, dehumidification, making sure that we're dialed in on the humidity levels for that space, okay? That's just kind of a high level of the HVAC design process. Before we even get there, though, we start with the location. Where is the building located? Right, it's the number one most important thing. Is this a house in Florida? Is this a house in Boston? Is this a house in Maine? They all have different, not only codes, but they also have different climate conditions. Siting and site constraints. What are the siting constraints that we're dealing with? Well, a lot of architects will talk about siting and making sure that it fits well on the site and it works well with the landscape, et cetera. We're doing the same thing, but we're doing it from an energy and a comfort perspective. If I can reorient the building, maybe 10 degrees, tilted the other direction, I might actually be able to reduce my cooling loads in that building. Right? I might be able to optimize the building by changing the window style, or window pattern, or the U value, or the solar heat gain coefficient of those windows. So the siting does matter, and some of the site constraints that we deal with. Utilities, right? Some buildings are still natural gas or propane or oil fired, right? What utilities do we have available to us? Is it an all electric system, right? Do I have solar, right? Do I have tall wooded trees and I don't have any solar access? These are the things that we're thinking about. Client goals and expectations. We have a client expectation sheet. It's on our website. We offer it to anybody that wants it. It's free. We just publish it. Feel free to use it. It basically asks the client certain questions, right? What are they trying to get out of this project? More importantly, what's their pet peeves? What are the issues that they're trying to avoid in this project? And then lastly, what's the budget, right? So we can try to pull that all together into a cohesive package that we can then have the chance of getting a successful project at the end of the day. Right? Without these things thought through, you will not have a chance of getting a successful project. Right? It's going to be really hard, right, to do that. So Manual J is in its 8th edition. They're actually working on the 9th edition right now. Here are some of the softwares that we use: RightSoft, HVAC or CoolCat, Quick Model, RHVC from Elite, Carmel, AdTech. All different versions of it, all have different pros and cons. But at the end of the day, what we're doing is a heat gain calculation. So we're picking, we'll talk about this, a 1% design condition and 75 inside. We do a summer snapshot and we do a winter snapshot of the building to figure out how much energy it needs for heating and cooling. Okay. So does anybody know the 1%, 99% conditions for Boston?
Will does. Is it 9 degrees?
What is it?
Is it 9 degrees?
So in Boston, it's 12.8 degrees right here for the 99% heating condition. No, it's not. Yeah, exactly. So it really depends on where you are. So Logan has a little bit of a difference. This is a great, by the way, this is a great website, ASHRAE Meteo. Just Google search ASHRAE Meteo, like meteorological. It's a free software, a free website that provides all of the published climatic data across all locations of the United States. So you can get Norwood Airport, you can get Hanscom Air Force Base, you can get obviously Boston Logan, you can get Worcester. Every airport's on there and other ones as well. So, and then the cooling is 1% at 87.7 degrees. What these mean is that 99% of the year, the temperature outside is either warmer or colder than these temperatures. So meaning in the example of 12.8 degrees in Boston at Logan, 1% of the year, basically 87 hours a year, the temperature might be lower than that. And the same thing on the other side, cooling, 87.7, there's gonna be 1% of the year, about 87 hours, that the temperature could be above that 87 degrees. A very common question I get is that, we're always 95 here. I don't care. I don't care about that. And people think that. But the reality is we're not at 95 degrees all that often, right? That's just the reality of it. If you want to play it safe, of course, you can try to use a different design condition, a higher, more conservative design condition. But you could go to the maybe 0.4 condition, which means 0.6% of the time you're above it, 90.8. And you can even look at the mean extremes, which is published here, of what it's been over the last 10, 20, 30, 40, 50 years, mean extremes, right? So I just want to give everyone an understanding of what these design conditions and snapshots are. And this is what it looks like. That winter scenario is 70 degrees inside, 13 degrees outside. So that's the winter manual J snapshot. We're going to get a sensible heating load. And the summer snapshot is 75 degrees, 50% RH inside, and it's 88, 72 degree wet bulb outside. And we have obviously heat gain being added to the building, heat and moisture. Okay? Everybody with me so far?
Yeah.
I know I'm talking fast and going through this, hopefully not too fast and hopefully not too slow. So what does that software do when you do a manual J? It's just it's calculating a load based on UA delta T. It's doing 1 million of these connectivity equations. And that means if I have a wall, I got temperature outside, maybe 88 degrees, temperature inside, maybe 75 degrees, I'm gonna have heat flow, I'm gonna have heat gain, heat transfer added to the building. And that's what that software is doing all across every wall, every window, every roof, every floor, every assembly in that building. Looks at the entire outside. And one thing just to be clear on, these are BTUs per hour. People shorthand it and call it BTUs, but it's really BTUs per hour. It's a unit of, it's like analogous to miles per hour, right? It's like a velocity or a speed, right? It's a rate of heat transfer, BTUs per hour. And so like I'm very much a stickler for units. BTU per hour matters, not BTUs. So the manual J looks at the U factor of all the windows, the skylights, the glass doors, the solar heat gain coefficient, how much solar heat comes through. Do I have any permanent shading, low E windows? I have to look at all the R values of all the opaque surfaces, internal gains, people, appliances, infiltration, how leaky the building is, HVAC system, the ventilation and the duct leakage, right? All that matters. It gets put in that software and we get a magic number, okay? We have an architect builder questionnaire also on our website. That's just to ask these kind of generic questions that we would want to know about the building. What's the air leakage target rate? What's the insulation of the walls? What's the R value? What's the U value? All those kind of things. We are starting to use a lot of AI and LiDAR in our business. And so if you're working on existing buildings and you want to do a manual J, there are two companies, Amply and Conduit Tech, that I'm familiar with that we use, where you could take an iPad, you could scan the building, and it creates a 3D model of the space, and it gives you a manual J in about probably 1/10 the time that it would take to normally do it.
Does it work?
Works amazing. We've done sensitivity studies. We've done it out the longhand way, and then in software, and then done it this way, and we're like literally within 5% each time. It's really amazing. And literally, you scan the whole room, just go right around, log it, hit OK, go to the next room, scan the next room. And you just have to set your, what's your average wall assembly, R value, window, U value. Then you have to, if you do a blower door, you can input that into the model as well. So it's pretty fabulous stuff. I mean, it has a monthly cost with it, et cetera, but if you're doing a bunch of these, it's definitely worth it. You're gonna define your zones, right? So once you have this manual J done, you gotta figure out how many zones of HVAC am I gonna have in this house, right? And zones are really, think about it, how many thermostats you're gonna have in the house. That's one of the starting points. You got to think about the building in terms of elevation, right? Basement, first floor, second floor, orientation, south side, north side. You got to think about those things when you're thinking about the zones. Because that's one of the issues that I see is that they have a zone that covers too much of an area, right? It either, let's say they did the basement and the first floor on the same thermostat. They put the thermostat upstairs or they put the thermostat downstairs and nobody's happy, right? Or a loft building. They put the one thermostat to cover 2 or 3 floors. And nobody's happy. You're either going to be comfortable on the first floor or you're going to be comfortable on the third floor, and you can't be happy either way, right? So that's always a concern. The next one is ventilation calcs. right? So for residential, they make it really easy. What's your square footage and how many bedrooms do you have? Really, really simple residentially. Commercially, like a building like this, we call this commercial, it's a lot more challenging because you have to pick your occupancy classification per zone or per area of the building. So we might define this as a conference, maybe a conference room, or we might call upstairs an office space, right? Maybe a reception area. Like we're going to define these spaces based on how it's going to be used. And that's going to tell us what the occupant density is, how much air do we need per person, and how much air do we need per square foot. That's outdoor airflow rates. We can do that math out.
Okay.
Humidification and dehumidification. Again, we're coming back to that chart. We can figure out what our humidification load is and what our dehumidification load is. Both if you think of that site chart, in the worst case winter and the worst case summer conditions for moisture. The reason I bring this up is because in the cooling side, here's our room air. Again, it's 75 degrees, 50% RH. Here's our peak cooling. That's our manual J, 1% condition. But guess what? That's our peak dehumidification. A lot of people don't understand that actually the most moisture that we have in Boston outdoors happens at around 80 degrees outside, not 90, not 88 degrees. So people think, oh, it's 95 degrees out and 90% relative humidity. No, that's not reality. 90 degrees at 90% humidity would be up here. It would be off the charts. That's not reality. But the reality is that our peak dehumidification happens at a time when we don't have our peak cooling loads. And when our thermostat runs, it runs based on this, on the temperature, not the humidity. Right? So this is why dehumidification is becoming more and more of a concern as we make the building envelope better. We reduce the cooling loads. By doing so, the system doesn't run as much as it used to. And on top of that, we have a peak dehumidification condition that is higher than what the HVAC system was sized for in the first place. Right? So that's a confluence of a lot of things happening all at the same time, but we have to be aware of it. So that's what our cooling system's doing. But this is what our cooling system might have to do, and that's why supplemental dehumidification comes up in a lot of projects now. And look at the different grains. 90 grains versus 115 grains. So we measure moisture in grains. I don't want to go into why that's great. It's a long story, but basically how many grains of moisture per pound of pounds of moisture versus pounds of dry air. That's the ratio, and that's what they call the humidity ratio.
Are you putting dehu in all of your projects?
Just about every one of our projects gets a supplemental dehumidifier.
Yes.
Yep. So manual S is system design. I'm not going to go through all of it, but basically when you have your heating and cooling loads defined, you have to size the heat pump, and it sets an upper and lower capacity on the HVAC system. So it doesn't let you oversize the HVAC, it doesn't let you undersize the HVAC, it puts you in the right spot. And the challenge that I see across a lot of HVAC contractors is that they look at the AHRI data, they look at the standard data that the manufacturer publishes. The standard data is at 95 degrees outside and 80 degrees inside with a 67 wet bulb. I don't know how many people live inside their house with an 80 degree set point in cooling. But that's what the data is. When you see the sales literature, that's what's published. That's not reality. So you have to go to the performance data tables for that HVAC equipment to give you what I'll call the real life cooling capacity for that equipment. Okay? Then you also have to do a manual D, which is a duct design, of course, if it's a ducted system, right? And it's just a calculation method. So hopefully this isn't too technical, but if you look at an air handler, this is an air handler, here's a return duct, here's a supply duct, and you were to map the pressure through that entire duct system, look at how it starts. It starts off at 0. So at the return register, if I measure the pressure, it'd be 0. If I start to move my pressure, my manometer, basically if I measure pressure along the way, my return gets more and more negative. I'm going negative here. So this is negative, right? It's on the suction side of the fan, right? So this is negative, negative, negative. Then I get to the return of the blower, and that's the most negative it will be. And then the blower does its job. It imparts static pressure. It builds the static pressure. And so this is the boost. The blower does the boost. So the highest pressure I'm going to see is right on the discharge of the blower. That's my highest static pressure. And then guess what? Then I have the decay all the way back to 0. So it starts at 0 pressure in the room. It goes through the whole duct system. It comes out at 0 at the other end. Did everybody see that? So when we talk about duct sizing, we want to make sure that all of these components, everything here, are mapped out and calculated for appropriately. So if you put in too restrictive of a filter, guess what? That drop right there is going to be massive. The filter drop is going to be too much. It's too much resistance on that air handler. The blower's going to struggle, right? If I put undersized ducting, if all this ductwork on the supply side is undersized, guess what? I'm not going to have enough oomph. It's going to cut out. It's going to cut down before I get there. I'm not going to get enough airflow into the room. Not enough CFM, right? So all of this stuff, it's a system. You got to treat the whole HVAC system as a system. It's all interrelational. I'm not going to go through the whole chart, but basically it says, what's my blower do? And then I subtract out all of my resistances. And I get a magic number in terms of inches of water column, in this case, 0.23 inches of water column. And another point that I want to make is the ductwork might be 80 feet in length from return to supply. Here's my blower, right? Here's my return duct, here's my supply duct, I run 80 feet. We're talking about total equivalent length of feet. Not 80 feet as the crow flies as I trace the line. I have to add up all the fittings. If I use a crappy fitting, that's 60 equivalent length of feet. That fitting represents 60 feet of straight duct. This fitting right here, 30. This one, 45. So if you think that the fittings matter, if I had a lot of fittings and a lot of crappy fittings, yeah, it does matter, right?
Friction measurement?
Friction measurement, exactly right. Yep. So the total equivalent length of this job might be 375 feet of actual total equivalent length, even though the duct run is only 80 feet. Everyone's like, it's 80 feet. No big deal. Yeah, 80 feet with the wrong size duct with a bunch of bends, that represents 375 feet on my blower motor. That's a problem, right? So trying to blow through one straw instead of trying to blow through 10 straws, right? A lot harder to go through that, right? So the resistance matters. So then you go to your friction rate chart, your ductilator. We call them fancy ductilator terms, one of my favorite words. And you basically look at your available static pressure and you look at your total equivalent length and you know what you need to design your ductwork for. So it's going to work right. That's your friction rate. Okay. And the last one is just air velocity limits, just making sure the velocity in the ductwork is quiet, right? And that's where velocity comes in. If I move the air too fast through the register, or if I move too fast through the ductwork, exceed these velocities, I'm gonna have noise issues. It has nothing to do with performance, just for noise. If I hear that rattle, that vibration, that humming, that's all because of this, right? So that's another aspect you have to review before you send those drawings out.
Don't you want kind of a loud system so people don't call you complaining?
All right, so we're gonna disregard manual T. We're going loud. We're going big.
Just put a whistle on it. Yeah.
An air horn every time it goes off. So just, manual J, manual S, manual D. Here's what a duct design might look like. Garbage in equals garbage out. So you got to make sure you're putting in the right information. And then we obviously didn't talk about ZR and LH, but obviously there are different manuals for different types of projects depending on where we go. But I'm going to stop there. We'll turn it over to Michael. All right.
All right.
Just a
That was awesome, Ross. Thank you so much, because so I'm an artist by training. Never took any physics or math to speak of. But when I started doing passive house stuff, just sheer dint of will, I had to try to learn this stuff. And I'm glad to say I didn't really miss the mark, but just being able to run through that was really great. And the fact that you pointed out immediately that there are all these different drivers of comfort, whereas to this day, okay, and I'm a dumb artist, right? But I was going into projects and they're saying, well, there's mold, but the cooling system should remove the moisture. I'm like, it's governed by a thermostat, not a humidistat. What are you talking about? Shouldn't we all know this?
Yeah.
But it's really interesting to dive into the fundamentals, and understand. And that was a fantastic experience. Thank you. All right, so I'm just going to talk a little bit about the barn, a little bit if I'm representing Nick and Amy, and I'm sort of representing their interests. So I'm the pain in the ass client in this case, as Peter suggested. Let's just talk about what I'm thinking about as a passive house guy. So, no, you didn't. I injected that. I'm sorry. Okay. Maybe I'm projecting my own, I don't know. Okay. Anyway, so this is cool. Nick's always a fun person to work with. He's so happy as he runs through sketches saying, okay, we're going to change this again this week. We do have a blast. Thank you, Nick. So yeah, it's going to be, as we said, the oldest passive house retrofit. That's cool. It's going to be a living design and construction lab, for those of you who don't know yet, and also the office for the Studio HPDC. And so what do? Well, I'm I and my staff got some really great people. We're doing the modeling for FIAS design certification. And this is our sort of workflow process of SketchUp to WFI model. And we're doing some consulting on the assemblies and the performance thereof. We're not the only ones doing that. And we're doing some building science analysis. We haven't quite got in, we're in our first round of FIAS review. This will be second round. But you know, the hygrothermal analysis and the thermal bridge analysis will be coming up quick. But this is a really special project for a number of reasons. One is that we're designing it as we build it, right? You're like building and we're like trying to keep up with the unforeseen circumstances. So the drawings keep changing, which is cool, and it's how retrofits go, and it's a real exciting process. A little frustrating sometimes. There are a lot of smart people that Nick has been able to attract to this project and have opining on, you know, various ideas about what we might do. So a lot of cooks in the kitchen, but everyone's super smart and cheerful about it. And it's like, oh, I didn't downsize that sketch. It's a sketchapalooza. Like we've got like, there are like 30 sketches in this montage that we're working through before we even have a complete set of drawings to run the energy model. So this is jumping over a little bit to Ross's domain, but it's just, I'm trying to think about this stuff. What are we doing beyond just certifying? What are we really doing? And that's trying to understand the dynamics of the building. So it can be a passive house, sure, but is that the goal? Well, if you're just a passive house, but people aren't comfortable, who gives a damn, right? So it's gotta be a good building in all the ways that Ross described. So we're trying to understand outdoor conditions and indoor conditions and how they relate to each other. So this is just output from some of our hourly simulation of much larger multifamily projects. But the idea that we're understanding hot water, heating, cooling, all the internal gains, et cetera, and understanding how the building sort of operates in these different extremes, but also all the hours in between. So when Ross said he takes a snapshot of summer and winter, in order to do an annual calculation, you need the whole thing. It doesn't make it a better model. It's for a different purpose, right? So what do we need to know the dynamics of the building? Well, this is from, there's a pointer here. What is it, this thing? Yeah. That's it. So this is from a project in New Hampshire we did, and I did modeling simulation to see what the internal gains are. So I had to take every internal gain and apply a hourly curve for it, and then, you know, we come out with, okay, here it is, what's the net? That's what's going on inside the building. So here, we're gonna have lots of people doing fun stuff, and it's almost never the same, right? So we're like trying to predict what this building will even be used as. And then so this isn't this building, obviously, but okay, what is this zone? You've already mentioned this, Ross. Zones act differently and they have different occupancy profiles. So within one building, you know, you'll have all these different things going on at the same time. And it's really important that we all recognize that the map is not the territory. And I heard that from Mark Rosenbaum when we were doing Wayland Passive House. When he came on the project, and I was saying, well, okay, well, this is the passive house thing. And he said, Michael, the map is not the territory. And then he said something else at a NESI conference, and he attributed it to someone else who I've forgotten. All models are wrong. There's not a single model that you could say is accurate to reality, but some are extremely useful for telling you the things you need to know under certain conditions. When you're in the map, if it's inaccurate, that kind of sucks. You'd like to have an accurate map. But if you're in the territory, you can't see the bird's eye view. So you need both, and you need to be trying to be as informed as possible with both. Okay, in other words, the intelligence of our perception is literally reality divided by the perceptual limitations, and the models all have limitations. So if you have a brilliant outdoors with millions of wavelengths of light, but you only have an eyeball that can see 2, that's all you see. So the evolution of our tools is important. The evolution of our mindset to understand how the tools work and how to see beyond them is even more important. Okay, so if we're looking at internal gains, what's going on? We've got, well, I'm sorry, I have all loads, envelope, solar, internal loads, occupancy profile. The occupancy profile is variable, seasonable, and you know, it's inconsistent, and we don't even really know what equipment is going to be in here. So we're making various assumptions. As I say, the map is not the territory. We make assumptions about it. It's not reality, So we build these tables of like, okay, how many people are going to be where? And Amy, thanks for sitting with Andy and going through all this stuff and just like saying, okay, on this day we're going to have this many people and then it'll spike. Now, this is really important because Ross mentioned ventilation. Well, you got 50 people in a space, that's a different animal from 2. But they're in the same building and the hours are swinging wildly in terms of the loads in the building for ventilation and the internal heat gains. So that's kind of cool. So, all right, so what our machines tell us, what can we see with our energy models and what can we not see? We can see exactly what we designed them to tell us and nothing more, unless we have intuition beyond that, right? And that's where good engineering comes in. Not being an engineer, all I can do is just sort of like blindly grope and then I call Ross, right? Okay, but what does passive, like everyone's saying, passive house, what a wonderful standard, right? And I've been doing it since 2009. I love it. It's all we've ever done is passive house and zero energy. I really adore it. However, it's really important that even us diehards realize what passive house modeling does not tell us. And it's a lot of the stuff that Ross is telling us, right? We're complementary. All right, so here we have, I showed you just a moment ago that we have this chart of all these people and all the equipment they're using, et cetera. We add that all up. And so we can see that in this building, in terms of our heating load, which is like the standard of care for Ross is middle of the night in January or something, right? Well, does anyone really care what temperature it is? Ross has to. I don't, if it drops a few degrees, right? But look at the internal heat gains. Itsy bitsy, because no one's here, maybe just some phantom loads. But for cooling loads, internal gains is like 85% of the load. If you are judging that on the evening event in August when you've got 20 people in the room, right? So you can see that for which load you're talking about, it's very different. For annual demand, look how much internal heat gains is. If we miscalculate, if Amy tells us you've got 3 laptops and you got a couple desktops instead, the internal heat gains inch up. Well, that adds up to a lot of energy over time. Okay, I'm going to try to go a little fast. So I hope you, yeah, right. And look at the cooling demands, the internal gains. These internal gains help us because they reduce our heating load, right? We're heating our own building. This hurts us. Am I being pedantic? Does everyone already know this stuff? I feel like I always find this stuff really exciting. Okay, what does passive house tell you and what does it not tell you? It tells you this. Oh, those are our average temperatures. Oh, there's our average relative humidity. Well, what is actually happening? Something way different. Like the averages are these smooth lines and they miss between the average here and the peak is double, right? So I lost a slide there, so but like there's supposed to be this slide, which is nice and smooth, and then the hourly is big and the temperature range is much more dramatic. And the humidity, as you were pointing out, is a huge part of loads, which has to be understood. And passive house will not tell you this. Any passive house consultant says, oh, I know how to tell you this. I mean, only if they're an engineer and are doing other calculations can they really say that with confidence. So this is a project in Washington, D.C. We put tuned shading fins on, okay? And like we were able to track the solar gain and the temperatures, and we were able to make sure that the solar gain was actually no greater in the summertime than it was in the wintertime. Because even though there was more available radiation in the summertime, we blocked it, you know, see, summer, right? So we were able to make the averages mean a little bit more. So the problem of averages, even if it's like daily averages, like this is the reality. And that's the thing that Ross has to be accountable for while we're like really happy with the top one, you know, great. We just heat it that much per day, whatever. Then the problem of latent loads. Even if you get the full hourly, which is double the average, then the latent loads are substantial. Another doubling in Washington, D.C. Now this is interesting, right? When I say, you know, the map is not the territory and our perception is our reality divided by our perceptual limitations. You might just say, oh, that's a nice philosophical conceit, Michael. You always have to have something, you know, philosophical to say about these issues. And I can say, okay, maybe it's not that important, except that if you learn, as I did the other day, that high performance heat pumps have a different coil design to deliver better sensible returns so they can have a higher efficiency rating. They drop out less moisture. And Mike Duclos, who worked with us on the Wayland Passive House, reported to me a year or so later, oh, this is the wettest year on record. And the humidity levels were like dramatically higher than the ASHRAE climate data. And that's happening in DC too. So then if you're right sizing, if you're really being constrained for right sizing your equipment, but you're not accounting for the latent loads and the sensible ratio, right? The sensible heat ratio, which is the amount of sensible heat versus humidity that gets removed. If that sensible ratio has to be higher to be more efficient, then you get less humidity removal. Now we're right sizing our system, as you pointed out. This is an incredible dovetailing. You're right sizing your system for the wrong load. So these are the kinds of things an annoying, somewhat informed client might ask Ross, but he knows the answers. All right, there are a few more things that I want to touch on. There are some things that we really need to, if I'm thinking outside of my limited model box by looking at hourly modeling, even though the certification standard does not tell me to, and he's thinking outside of his box of snapshot summer, snapshot winter, okay, and we're trying to think holistically, which is what good teams do, then we might be able to talk about load sharing for more efficiency, right? Oh, well, you got a hot water load and you've got a low heating load. Oh, you got a big cooling load. Hey, what about combining them and seeing what happens? You might be able to talk about how refrigerants are a driver of climate change, or your indoor air quality concerns, climate resilience, hazard mitigation. Those are all very closely related. So on this project, we're actually trying to think about these things. This is another project, but here's my domestic hot water load. Here's my heating load, but I can add 30% to my heating load. In this case, that was really important because it was a cooling load dominated building. So I'll do a little extra in the wintertime and I can reduce my cooling load by taking the heat from the air and putting it into the water. So this is where our cooling loads get reduced. So then we're able to balance the system. So refrigerants are a huge driver of climate change, and the world needs a lot more refrigerant now because we got a lot of people in the global south who are going to die from high wet bulb temperatures. And here we are, super thrilled, super honored to be able to work on 11 Lennox in Boston, which is the first mass timber bottom-up construction in Boston. We're super proud. And we kept going to them saying, hey, how about another kind of heating system? Because they want to do VRF. VRF is a monster when it comes to refrigerant. Refrigerant is one of the leading causes of climate change, and it leaks to the tune of whatever, 3 to 5% a year. So we looked at geothermal. Well, here's the operational carbon. Here's the refrigerant leakage. It's very small because it's a packaged system. And then there's the embodied, okay? But if you go to VRF, look at that. Operational energy is a bit higher, but the refrigerant leakage, carbon equivalency is dramatically higher. So VRF system, it's our go-to solution, right? Super efficient, super zoned. Everyone wants to do it. I don't know. Like, I've been sick to my stomach since the first days when we're like, oh, this got great new technology. Really? All right. Another thing we might do, and I'm going to shut up in a sec, is we could be thinking about climate resilience and hazard mitigation. Ross already mentioned that your comfort is better when you have a better thermal enclosure. Well, you can also last through a winter power outage and the temperature starts to drop. Over the course of a week, you never get below 60 degrees. That's pretty resilient. In the summertime, not so much because you got internal gains in solar driving you up, but that's when we have plentiful solar energy. So we can size our battery system to account for operating over an extended or indefinite period if we reduce our loads. So we can define a critical load zone, and we do an intake form where we say, okay, this thing, is it a critical load? You know, are we, which zone is it in? And we kind of get an owner's sense of how the building needs to function in case of emergency. That's another thing we could entertain here. And then you provide backup power based on that. How much can you afford to keep as a critical load zone to drive resiliency, to extend your resilience? All right, that's it. So those are our, that's our like client charge to the engineer. So I'm gonna hand it back to him.
Ready? Let's start, Michael.
Does anyone need a drink? I'm serving.
We doing a break or we going right into it?
We can go right into it. I was just saying.
Keep going? Okay. All right. That's right. That's right. Thank you, Michael. That was great. That was great. All right, so we got two parts to this next bit. First one is HVAC system options, just kind of high level, what are the options out there? And the second part is about the barn specifically, doing a deeper dive in the barn. So just real high level, right? You can move heat with water, air, or refrigerant, right? You have sources that generate the energy. You can transport it through piping, through ductwork, or through refrigerant piping, and then you have emitters, like a register or, mini splits or, fin tube. So all different, I think of it as a tree. I gotta generate the energy, I gotta transport it, and then I have to emit it, right? So that's the way I think about every HVAC system. And you can blend these. You can take this one and put it with this one and put it with that one. You can take this one and put it with this one and put it with that one. You can put it, you know what I mean? These are all kind of interchangeable in terms of how they come together. But that's the essence of it. So heat pumps. Everybody loves heat pumps. We talked about VRF. That's the craze right now. We're gonna talk about there are other options to consider. So first off, heat pumps. They are all measured by source and load. You have air-to-air heat pumps. You have air-to-water heat pumps. You have water-to-air, water-to-water, right? So these ones would be geothermal based. This is an air-to-air heat pump. Everyone calls it a mini split, right? Right? And then there's also geothermal, water-to-air. To put water pipes in, I get air blowing out in the ductwork. Here's water-to-water, right? Water goes in, water comes out. This is the geo loop going in. This is the heated and cooled water coming out. Here's an air-to-water heat pump. Right? Air goes in, hot water or cold water comes out. I can have a package or split. So what's the difference between this and that? That is a split system. This is a packaged heat pump. Packaged, split, hence mini split. Let's make it small, let's split it apart. Brilliant, right? Mini split.
Meaning that both functions of the outdoor unit and the indoor unit are packaged into
The outdoor
that.
unit and the indoor unit are packaged into one box. Right? And then this is a split unit, meaning the outdoor unit and the indoor unit are separated apart and then connected with a set of pipes between the two.
They call these ones mini splits. Why don't they call big ones maxi splits?
Great question. I don't have an answer.
I think we should talk about that for the rest of the night.
Yeah.
Can we? Yeah.
I don't know. That's a good question.
Need more beer.
Mega split.
So mini splits have different flavors. Variable refrigerant flow, VRF, is the broad category. It just means it's varying refrigerant flow in a system. There's one-to-ones, there are home runs, multi-splits, there are branch box, right? They're all different pros, all different cons. These are options, right? I think of them different tools in the toolkit. They all have pros, they all have cons. You can go VRF heat recovery, right? Got bigger branch boxes, outdoor units, branch boxes. Now you can do simultaneous heating and cooling. Right? That's another flavor of VRF, a different style. You also have central ducted heat pumps where I have an outdoor unit, an indoor unit, and I put some zone dampers on it. Those are gates that open and close to deliver air to a zone that needs it. Right? That's a central ducted heat pump, a central split heat pump. You have small duct high velocity, another different tool in the toolkit. Pros and cons, but again, snaking small tubes at a very high pressure to send out really high jets of air, high velocity into the space. There's also air-to-water heat pumps. It's the new kid on the block in the United States. It's actually old school if you go to Europe and other parts of the world. But the understanding here and the reason we've been designing air-to-water heat pumps for about 15 years. So it's not new to us. And so the reason we like air-to-water heat pumps is for a bunch of the reasons that Michael mentioned and some more. So first off, with air-to-water heat pumps, I can provide heating, cooling, and domestic hot water. I can do all three. Right? I get a 3-for-1 with that approach. I get heating, cooling, and DHW. It's a magic box outside that does all three. I can do it in retrofit and new construction. We'll talk about that. It's less refrigerant volume. That's a big one compared to VRF right off the get-go. Okay, so this is what's installed. This is a single tank that comes hermetically sealed like a refrigerator in an air-to-water packaged monoblock system. This is how much refrigerant I need in the equivalent of a VRF version of that. So if I have a refrigerant leak, which one would you rather have leaking? Right? Less refrigerant volume that has a bunch of embodied carbon aspects to it, operational carbon, etc. Has a big issue with the ozone and global warming potential. Self-contained package, no refrigerant in the building, no trim charge. I can't tell you how many times I go to an HVAC job that's gone bad, and it's because a flare fitting has failed and it's lost all its refrigerant, right? Or a big part of its refrigerant, right? So I don't have trim charge with air-to-water heat pumps. There is no trim charge. I don't even have to touch the refrigerant. I don't even have to bring out gauges. When you buy a refrigerator and you call the refrigeration technician to come fix it, it comes pre-packaged from the factory, hermetically sealed. In a factory, that's the same thing with air-to-water heat pumps. Packaged. All comes from the factory. I don't have to interject at all, because as soon as I hook up my gauges to it, I now have an issue. I could have moisture contamination, outdoor air getting into that system, a potential leak, a bunch of issues, right? So we want to make sure if we can avoid that, it's going to make our lives easier for the HVAC contractors as well. Refrigerant phase out. It's not an issue. I think you guys have all probably heard about R410A going away, right? Being replaced with A2Ls, with R32, R454B, these mildly flammable refrigerants. If I have a failure of a 410A system, and let's say the air handler fails or the outdoor unit fails, I have to replace the entire system. The new refrigerant is not compatible with the old systems. So I have a brand new system going in a house. Let's say it's 410A system, split, outdoor unit, indoor unit, refrigeration lines in between. My air handler, let's say, fails. I can't get a part. You're telling me that I have to replace the indoor unit, the air handler, the line sets potentially, and the outdoor unit? That's a problem, right? Sometimes you can reuse the line sets, sometimes you can't. I don't have that issue. My air-to-water heat pump fails, I rip the box off, I put a new box on. Okay? Distribution piping can be plastic. I can use PEX, high-density polyethylene, polypropylene. I can use copper. I can use any piping material that carries water, no problem. No risk of former carry corrosion, galvanic corrosion, obviously because it's all plastic piping. I have less penetration to the building exterior. All those line sets that are coming in, I got just one set of pipes. That's it. Question in the back?
So air, water, heat pump in cooling mode, how do you manage dehumidification?
Hold that thought. Hold that thought. Yep. System is expandable. Just like you're adding a bathroom to a domestic water system, I can cut into the pipes. I can add a domestic cold water line, a domestic hot water line to that new bathroom. I can do the same thing if I add a zone to an air-to-water heat pump system. Just expanding the pipes. It's just water. Right? It's compatible with energy storage. I can use buffer tanks. I can use phase change material. I can do load shifting and time of use rates. Time of use rates are coming. Right? So the idea with time of use rates is that they charge you different amounts of energy, a cost of energy, right, at different times of the day. So if you want to use your cooling system at 2 in the afternoon and it's at peak rate, you're going to pay for it. It might be 40 cents a kilowatt hour, 50 cents a kilowatt hour. But if you use your compressor and you use your air conditioning system at night when power is cheap, guess what? I'm going to charge you 9 cents a kilowatt hour, right? So they're going to penalize you for using cooling, or that in this example, at certain times of the day. If I have buffer tanks and phase change material, I can load shift. I can run my compressors at night when power is cheap, store it in that battery, the thermal battery, and then use it all during the day, the next day, right? So it becomes with economies of scale, but this is coming, all right? They do time of use rates in California already. They do it in Vermont in many areas. They do it in some parts of Texas. It's coming. Yeah, it's definitely coming. Because the power plants, they're incentivized. They're incentivized that they have to do this. They have to do this. And it's synergistic with solar PV. This all runs on electricity. So if you can add solar, you can now produce the energy that the compressor in the system uses as well. Okay. The new ones that I really like that are coming from Europe that haven't been approved yet, which are coming, are R290. R290 is propane. It's right here. It has a global warming potential of 3. Compared to R32, which is 675, compared to R410A, wherever it is on here, it's 2,000. Right? So we're going with better refrigerants, natural refrigerants, lower GWPs, better efficiencies. The only downside is R290, everyone gets scared because it's propane, it is flammable. Right? But it's outside self-contained.
You mentioned the refrigerant phase out being a non-issue for this system in particular. I mean, they're still making replacement parts for 410A.
Yep, they're only obligated to for 7 years. Yep. So after 7 years, you might have you could have a small component fail in an R410A system. Could be a control board, could be an EEV, could be a expansion valve, could be a blower, and you might not be able to get that part for that system. And if that happens, what do? You know? So that's a problem. So what does the air to water look like? There's a million ways you can pipe it, right? I'm just going to show you one example here. I can have an air to water heat pump outside, 2 pipes coming inside. Guess what? I'm doing domestic hot water, I'm doing heating, and I'm doing cooling. I can do 2 pipe fan coils, 4 pipe fan coils. I can do radiators. I can do radiant floor heating. I get domestic hot water, I get heating, and I get cooling, all from the same system. So the system can heat this buffer tank up, then the diverting valve can flip, and it can make chilled water, and it can send chilled water to that air handler. The chill water can do cooling and dehumidification.
You need another storage volume? You had one storage volume. Do you need
Yeah,
another
so
one
we'll
for
show you
cool-
another one which has 2 buffer tanks, one for cooling, one for heating. Yep.
Okay.
So you can do ceiling cassettes, you can do wall mounts, you can do horizontal pancake units, you can do vertical air handlers, you can do panel radiators, you can do radiant floor heating. You pick and choose what you want, right? The heating and cooling emitters for these systems, pretty much anything you want.
Can you retrofit onto the existing slant fan?
Yep, you can retrofit onto an existing slant fan with some caveats. Yep, yep. This is one of the caveats. So when you have a heat pump, it does a really good job of generating low temperature water. So if I have a heat pump, an air to water heat pump, and I'm asking to deliver 95 degree water, it does it with a COP of anywhere from 2.7 to 5 based on your outdoor temperature. So if I look at the 95 degrees, this is the 95 degree temperature at different outdoor temperatures. So at -4, it's still gonna be at a 2.5 COP, right? Amazing, right? If I have to jack it up to 131 degrees, my efficiency's hit, I go to the black line. So I'm gonna go between 1.9 at 5, all the way up to 3.2 at 47. Still better than your traditional, mini splits, but it's not as great, right? Not as advantageous. So the key for us is to get the water temperatures delivered to the space as low as possible to still heat the space in heating mode, right? And same thing in cooling, to get it as high as we can with chill water temperatures so we can get the best efficiencies in cooling. I'll do a bunch of questions at the end if you want to hold it. So what are the things you got to be worried about? One is that the piping has to be insulated because it will condense, it will sweat, right? Because chilled water could be at 45 degrees, could be below dew point. So you have to have valve wrap kits, or you have to have PEX that's pre-insulated. They sell rolls of it. You can then snake it through. They have these things called clamshells that wrap around the pump so that this doesn't happen, right? And they have insulation that can be continuous throughout. So that is one big caveat. We got to make sure the pipes are well insulated when it runs in cooling mode, right? We're only talking about 1/2-inch wrap. We're not talking about a lot of insulation, just 1/2-inch wrap, and you're going to be good for up to 80 degrees, 50% RH. So pretty high dew points. You can either 3/8 or 1/2-inch depending on your pipe size. So here's some examples of projects that we've been a part of, either designed, consulted on, etc. So here's some LG air-to-water heat pumps. Here's an Enertech unit. Here's a Space Pack unit. Here's a Viessmann unit. Here's some buffer tanks. There's a chill water buffer tank. There's a hot water buffer tank. All of these are doing heating, cooling, domestic hot water. All of them. You can also do split systems. So here's the outdoor units. Here's the indoor units. There's our buffer tank. There's our heat pump. Here's our Zender ERV on the project. So you can do package, you can do split. All right, let's dive into the barn. All right. So we modeled the barn, and here's some of our assumptions, right? So we have wall insulation, roof insulation, windows, air tightness. Right now, we're just looking at the heating and cooling loads. We're assuming no DHW or minimal loads there. Future solar PV, no fossil fuels. That was one of the things that the client had asked for, is basically to try to go all electric. We've got basically on the first floor 3 rooms. Basically, it's this main, we'll call it the conference room, and then we're gonna have basically 2 bathrooms off to the side there. We'll talk about the internal gains. People, computers, some lighting. Second floor, 2 rooms, 2 offices with 4 computers, a couple people, computers and lighting. We'll talk about these people loads and why they matter based on what Michael just talked about. I'm not gonna bore you with all the kind of the assemblies, but let's start about ventilation. So if I look at the code minimum, if I define this room that we're in right now as a conference meeting room, the code's gonna tell me that my population is 55 people in this zone.
We're pushing that tonight.
Might be. So if I define it as an office, upstairs as an office space, it's 541 square feet, it's gonna tell you it's 3 people. The occupant density is set by the code minimum. You can always increase it, but they don't want you to drop it below the code minimum. But this is where art and science meet, because you could define this as an office space, and that would drop the people load down to like 12 people, right? So this is where the engineering, the art and science comes together. What is this space going to be defined as? And that's a client conversation, and that's trying to understand what that means. But the load right now is based on this being a conference room, defined as a conference room, which means it's 55 people. Guess how much ventilation we need? 425 CFM. And upstairs is an office space, 541 square feet, 3 people, 57 CFM upstairs, based on the commercial code and these defines. We need 25 CFM continuous for each bathroom, or 50 CFM intermittent for the 2 bathrooms that are going to be over there. With me so far? Okay, breakdown. I think Michael already mentioned this, but do you think this load of this building is heating dominant or cooling dominant? We're in a very cold climate. Is it heating dominant here or is it cooling dominant in terms of the loads in the space?
Heating.
Heating dominant, right?
Oh, I thought I was gonna be wrong.
Is it heating dominant or cooling dominant?
Internal gains are pushing to it cool.
So you would think most buildings in a cold climate like Boston with a 13-degree temperature and only an 88-degree outdoor temperature, it's gonna definitely be heating dominant. Not this building. The heating load, 23,000 BTUs. Cooling load, sensible cooling, 33,000, plus this little thing called latent cooling, another 15,000. So I have 49,000 BTUs of cooling, 23,000, it's almost double.
Which occupancy class? Is that as an office or as a?
This is office upstairs, conference room downstairs.
So that's assuming the
Assuming there's 55 people in here all the time?
It's the snapshot is the summer condition, 55 people in here, fully ventilated based on the code minimum. That's what gives you basically a 4.2 ton, a 49,000 BTU load. Look at the cooling load, right? The ventilation, the walls, the glazing, the ceilings. Look at all the percentages. It's dominated by internal gains. And the internal gains is the 55 people that are all giving off heat because we breathe, right? We give off water vapor, right? We have latent load and we have sensible load. Each person that's sitting right now, each person is giving off 230 BTUs a person of sensible and 200 BTUs of latent. Because we're breathing.
Sensible and latent from a human is like basically equal.
Sensible is to about 230 for a person at rest, sitting in a chair, and 230 sensible, 200 latent.
Yeah, but like about the same.
About the same.
For all
Close.
intents and purposes.
Yeah. Yep. And if you're doing light duty, it'd be like 275, right? So you can look at the charts to figure out they've tracked this, right? And so you can figure out based on your activity, you can figure out how much heat you give off. But people give off heat. 55 people, it's a lot of heat. You're almost 2 tons almost of cooling just for the people.
In the worst case scenario.
In the worst case scenario. In the summer.
Not allowed in here in August.
But this is the reality of it, that this type of building in a highly occupied space is very different than a house. Yeah. And the math tells us why, right? Same thing in the heating months. It's all, the building enclosure is actually really good. It's unbelievable. The ventilation load represents 50%. Right? And the load, actually, you can make the argument that load is actually going to be less because if I have people in here, 55 people in the wintertime, we're going to be giving off heat. The heating system isn't going to run as much. Right? So it's it net helps us in the wintertime, but it hurts us in the summertime. Okay? So what's the room by room breakdown? Well, the open office area is about 1,000 square feet. You can see the heat loss and you can see the total, sensible and latent right here, 21 plus 13. You can see the totals, sensible and latent. So you can see the percentages of breakdown in terms of which rooms are the problem rooms. It's dominated by this open office space, the conference room, what we're calling the conference room. And then upstairs, manageable loads, right? The office space is upstairs, manageable. 3 people in there, not a big deal, right? So if I was gonna do a simple solution here, that was an air to water variation, that was gonna do heating and cooling, this is what it would look like. I would have a unit outside, 2 pipes to a buffer tank, and that buffer tank would do fan coils, a fan coil for upstairs and a fan coil for downstairs. If I want to get a little bit more creative, I can add some radiant floor heating, some panel radiators, and be a little bit kind of sexy with it. I don't have to. I could just use some fan coils and just call it a day. Right? Put a fan coil for the first floor, thermostat down here, fan coil upstairs, and thermostat upstairs. All connected to one buffer tank, and then it's going to have a switchover between heating and cooling.
When you say fan coil,
Yep.
you say like, what do you mean?
Yeah, I'm going to show you what it looks like. Yeah. Well, yeah, actually, I'll go to this picture just because
This picture is actually better. Would both those fan coils be within the conditioned space?
So this right here, or this right here is what I'm talking about. Either this guy, a vertical unit, or horizontal. So I'm thinking on the first floor, vertical unit with ductwork exposed here. I'm thinking upstairs, either a pancake unit or this on its side, a smaller version of that, but on its side, doing the upstairs. And we'll talk about that.
In the conditioned space?
Inside the conditioned space. All the air handlers are inside the conditioned space. Yep, great point. Okay, so that first floor air handler, here's my sensible load, here's my latent load, here's my total cooling. It's about 3 tons of total cooling. I go to the chart, I go to cooling performance, I look at my unit, 45 degree drinking water temperature, 75 degrees. I come down, total cooling, 29,000, sensible cooling, 23,000. 23 meets my sensible load. That's that. That's 1,200 CFM on a 3-ton unit with 6.5 GPM of water flow going through it. But I'm a little short on my on my latent. I'm short on my latent. And the reason I'm short is because I got 55 people breathing, giving off all that water vapor. So because of that, I'm short on my sensible capacity. Even if I went upsize, even if I went to the next size up, I'm still going to be short. Dehumidification in this room will be needed. A supplemental dehumidifier will be needed. If you have 55 people in here, the humidity is going to rise. The cooling system will not be able to keep up. If I don't care, maybe the client doesn't care about the relative humidity for that short period of time rising, then maybe we can get away without it. But in reality, we should have it.
Crop tops.
Feel free.
What's the, if we look at pints per hour, I know this is a commercial system, but thinking about some of the mini splits, how low they are.
Yeah.
These types of systems, air to water, what does that look like?
Let's do the math out right here. So you want to know how many pints per day this unit's going to run when it operates at these conditions? So I'm going to do the math. So it's going to be 29,100 BTUs minus 23,700. So this is basically total cooling minus sensible cooling. The delta is latent. So that's 5,400. So the delta, right, between, basically, yeah. So we need 13. I'm short by 8. So it's 5,400. I'm going to divide by 1054, and I'm going to multiply by 24. That's about 122 pints per day. So when this unit's running, it's going to give me about 122 pints per day. Good amount. That's like 155, 160 nominal pint per day dehumidifier. Like a Santa Fe, 160. Yep. Second floor, here's my sensible load, here's my latent load, total cooling. The smallest unit easily does it. And I don't have supplemental dehumidification up there. I don't need it. I'd meet the load up there because I don't have as many people. My latent load is much, much more manageable. I have 3 people or 4 people up there, right? Not a lot of ventilation load, not a lot of latent load. Right?
Are you counting for the spaces being connected? Does that matter? It's an open stairwell.
Yep.
So does this heat and humidity get up there?
Yeah, so I'm defining the open space as this open space in the first floor zone, the bathrooms, and the stairwell going up the stairs. And then at the top of the stairs, the second floor system picks up. Yep. But you will get a little bit of stratification going up the stairs, up and down. But we have a thermostat upstairs, we got a thermostat downstairs, so we'll be able to keep that. And then obviously the dehumidification load will be here, which will be picked up by the dehumidifier.
And controlled by a humidistat.
And
in
controlled
this
by
space.
a humidistat.
So it
yeah.
wouldn't even necessarily have time to get upstairs.
So the idea is that the thermostat is controlling both the air handler for heating and cooling, but also it has a dehumidification function that turns on the dehumidifier when it needs to. Yep. Yeah, it needs to have control and sensing of the humidity in this space. Yep. Okay, so how would I handle the ERV in this space, or the ventilation in this space? The peak outdoor ventilation rate is 482 based on all that people, right? 425 for the first floor, 57 for the second floor. So what would I do, right? And this is again where the art and science blend. Here's the way I would tackle it. I would recommend 2 ERVs, right? And the first ERV, I'll call it ERV1, will be steady state, the everyday rate. I'm gonna design that for 5 people in the building. I'm gonna ask Nick and Amy and Michael, how many people are in this space most of the time? Let's say it's 5 people. That's gonna be 160 CFM. So the first floor is going to get 100 CFM of ventilation air, second floor is going to get 60. So I solved the second floor ventilation with that unit, and I solved the everyday use case for the first floor space. 160. I also use that unit to do my bathroom exhaust. So I killed 2 birds with 1 stone. I get my ventilation and I get my exhaust for my bathrooms, right? And that will handle most of the conditions for the ventilation for this building. But then I add a second ERV, and the second ERV is for supplemental ventilation based on large gatherings. The only time it's going to kick on is when a CO2 sensor in the back senses that the CO2 is rising in the space. And when it does, it's going to have the ability to boost up, in this case, to 322 CFM. It's only going to be designed to run when it needs to, based on demand control, based on when there's a large gathering in the space.
Good news, you can all come back in August.
You're back. You're good. You're good. So based on CO2, it would handle the first floor only. Okay? We could talk about MERV 13 filters. We could talk about pre-filters, right, for dealing with wildfire smoke and other issues and things like that. But that, just high level conceptually, that's what I would recommend for this building as a ERV strategy and ventilation strategy for it. obviously here's the first floor plan, here's the second floor plan, kind of I was laying out, and I've got some thoughts in terms of how it's going, how the systems would actually be laid out. We'll come back to that in a second. And then a lot of people ask me, well, how would you duct these systems all together? This is just a kind of a conceptual snapshot that I can have an air handler with a supply trunk and a return trunk, and I can add, let's say, a media filter, I can add a HEPA filter, I can add a ventilating dehumidifier, I can add an ERV, I can add that all to this system to make it what I call like the ideal or optimal HVAC system for the space. And that's all I got. We'll open up for discussion. How about that? That sound good?
It's awesome.
Who's got all those questions? I saw some hands in the back and I wanted to keep moving just for the essence of time, but. Yeah, Brendan, yeah. What?
I guess one question is, you mentioned there's all this discussion about cooling systems being designed primarily for max sensible and for max efficiency.
Yep.
Like, is anybody doing anything else? Because clearly we need something else. We need something that's better with latent. And I would imagine the answer is no, but I'm curious.
So
Yeah, I want to show you.
you can slow down with different air handlers. You can slow down your CFM specifically for latent removal.
Yeah.
I've done a lot of this using. I'm partial to the space pack air handler. iFlow has one that lets you do it too. You can really crank down the airflow based on a latent load. They'll take a separate demand call from your thermostat or whatever, right? However you're calling for dehumidification, and they'll run a fan speed that you can designate. So in my personal house, on a call for dehumidification, I keep my coil at 44 degrees. I run about 260 CFM through my house, which isn't enough to actually cool it, but it does dehumidify quite well.
So if I look at like a Mitsubishi, unit, I look at its performance chart. So if I look at most of the operating conditions, I look at sensible heat capacity and total capacity. If I look at, let's say, 90 or 95 degrees, you see how close these numbers are? So if I look at this unit, it's going to give me 22,000 BTUs of cooling total, but it's going to give me 19.7 thousand BTUs of sensible. So the sensible heat ratio, if I do the ratio of the 19.7 into 22.5, it's 89%, so it's 90%. So meaning that if I run this system, 90% of it drops the temperature of the room, 10% of it drops the moisture in the space, right? And the trend is that all these manufacturers of mini splits, inducted splits, they're going to higher and higher sensible heat ratios. And the reason they're doing that is because they get better brownie points. They get better SEERs and EERs. Right. So the rebates offered by the utility companies incentivize manufacturers to go to higher and higher SEERs and higher EERs. So what they do is they say, hey, I'm not going to run the compressor as hard, and I'm going to warm that coil up, and therefore if the coil is not as cold, it's not going to wring out as much moisture when it runs. So these heating and cooling systems that are now offered with ducted mini splits and VRF strategies, the problem is that they're becoming terminal cooling units for sensible only. They're not doing any moisture extractions. Right?
Yeah.
And so we have a job where I did the math out. When it runs at a 0.94 sensible heat ratio. It removes 1.1 pints per day. Like,
so the
freaking kidding me?
Yeah, so the myth that we have dehumidification when we have a cooling load is just blown apart. And like, I remember not being an engineer or an architect or anything, and I went to building science summer camp or a building science expert session in the winter, and then I got Andy Ass' book.
Yeah.
And the rule of thumb is 70%.
Right.
Is a sensible heat ratio of 70%.
So yeah, and Jason will tell you this. So if you look at the capacity, if I look at 45 degree entering water temperature, and I could drop that by the way, but if I just look at that, what I can do is I can change the fan speeds. So I could put in a large box and I can run 45 degree chill water temperature through it, and I can change the flow rate through that coil, and I can drop the air handler speed. And by dropping the air handler speed, I'm allowing that air to go across that coil, and I give it more contact time. The air sits on that coil longer. It's a cold coil. It has a chance to actually wring out the moisture and dehumidify, and that goes in. So the sensible heat ratios on all of these products are 0.7, right. 0.75, even 0.65. I can do a space pack or a Unico, and I can get down to 0.6 sensible heat ratios. 0.54, exactly.
And what I would want to throw into that conversation is I'm from Baltimore. We do a lot of work up here, but I'm also doing tons of work in North Carolina, DC, and like, look at me, I'm your future. Like, hot and humid is coming north. So that's a scary thought, me being your future, but it's true. And we get, I was just talking to a rater day before yesterday, and he said, oh, no, it's the cooling loads are going down. We're shifting into September. It's just like mold calls every day, all day.
Right.
Because of this problem where the VRF systems in particular are so good at sensible that the former assumption, which most engineers are still carrying in their heads, that, oh, you got dehumidification when you got cooling. Now, I already had a problem with that because we've got these beautiful long shoulder seasons in the mid-Atlantic when it's lovely out, but it's high humidity. So like we got no cooling load and it's sopping wet. So if you don't have dedicated dehumidification, particularly when you have a passive house in an ERV that recaptures 40 to 60% of the humidity, like your humidity is just like you really need to be thinking about dehumidification. And so this is one of those things where the unforeseen, unintended consequences, right, of being super efficient and being like energy minded actually started kicking us in the butt. So Ross, I'm not smart enough to do this, but you probably are. If you've got a unit that could operate at a 70% sensible heat ratio, okay, then that's going to have an energy load. Some of it is going into dehumidification.
Right.
If you don't have that, you have to plug in this other thing.
That's right.
Do we have an understanding? Is it more energy to have this separate system doing the load that the cooling coil could have? It'll be higher embodied, right?
Higher embodied, higher upfront cost, more equipment.
Operational will the operational energy also be higher?
Santa Fe's going to run like a 12 amp circuit. You're going to use anywhere between 8 and 12 amps on a Santa Fe, depending on what size it is, that you're throwing on top of your cooling load. Where, generally speaking, my space pack, or pick your brand, whatever your brand choice for your air to water heat pump, if you're running a big enough buffer tank, you can chill that buffer tank and you can drive that temperature down. You can just continue to, you're using a circulator that's pushing, I call it 70 watts maybe. And then you're using your fan is ramped way down. If you're only pushing 200, 300 CFM, which is about as low as you're going to want to go for, or about as high as you're going to go for a typical house if you're just handling latent and not trying to cool it.
Yep.
You're like what, 3 amps maybe? So you're 10 amps in total on your air to water system and your air handler versus 13 for your, or 7 to 13 for your Santa Fe plus your air conditioner.
Yep.
You're drawing more energy, doing with more equipment, more capital expenditure, and not really doing it as well.
So we're gonna do an experiment here. What we'll do is we're gonna plug them in, and we'll track them on, and that's part of the laboratory.
There you go.
Right.
Let's run it in 2 different modes. We'll run a Santa Fe and we'll run the air to water.
Yeah.
So I think
Yeah.
you just answered my question, but I just want to double check with you. So the added equipment, the added amperage, okay, et cetera, added cost. But if you have these two in the same machine, is it ultimately net more efficient than having a super high efficient, sensible, and then a separate dehumidifier? Is it automatic that it's the net would be better to take a hit on the sensible efficiency?
Yes.
Okay.
Yeah. Yeah. The net overall efficiency, if you can run a air to water heat pump as opposed to a ducted dehumidifier that has the ability, because you think about a ducted dehumidifier, what it's doing is it's running a compressor to make a coil really cold, but the coil is rejecting its heat to the downstream coil to make it
Warm it up again.
Warm it back up. So what it has to do is it basically is make the coil really cold to get the warm air and the warm air that's really moist to dehumidify, and then go reheat it back up, and then send that 90-degree dry air back into the space. The cooling system has to catch up.
Which actually has to.
So the net of that is that you actually are hurting the energy. You have an energy penalty with it. But if you don't have a system that can do it, you have no other choice. You have to play the game. You have to use a ducted dehumidifier for that.
Right.
So, but if I can play with the sensible heat ratios, which I can do with chill water, that's what they do in commercial systems all the day. They've been doing it for 100 years.
Wow.
If I can change the water temperature and change the water flow rate and change my air handler flow rate, everyone's always been fixated that air handlers have to be designed for 400 CFM a ton or 350 CFM a ton. They always say, oh, it's going to be 400 CFM a ton. That's with a traditional refrigerant-based system. With chilled water, I could run 200 CFM a ton. I could run 150 CFM a ton. I don't have a risk of a frozen coil. The whole idea, oh, my coil is going to become a block of ice. That's not a thing anymore. Because the chill water temperature is running at 45 degrees.
So that's why they were doing the 400 a ton to move enough air to keep it from freezing with the refrigerant system?
It doesn't get cold enough.
Right.
Yeah, it doesn't get cold enough. Right? Where a DX system will get colder and colder and colder and colder, and then you get less of the airflow, and then you get ice formation because you're at 32 degrees or very close to 32 degrees, and then it becomes a block of ice. Yeah.
Yeah, for the slow kid in the class, can you re-articulate sensible and latent?
Yeah. So when we measure BTUs, right? When we look at air has a sensible capacity to it, and it has a latent capacity to it. And what I mean by that is that there's water vapor in the air. And the air conditioning system sees both the kinetic energy of that air, meaning how much heat is in that air, the sensible aspect of it, but it also sees the water vapor in the air. We don't see it, but it's there, right? And so not all BTUs are created equal in the sense that if a system has to run in cooling, I have to drop the temperature and I have to drop that water vapor. I have to dehumidify. And it's much harder to drop water vapor, much harder. So latent capacity is a Latin term for hidden. It's hidden, right? We can't see it. It's there, but it's hidden. So latent capacity is hidden BTUs that are stored in the water vapor in the air. And so we need to wring that moisture out. We need to dehumidify, and that's the latent capacity of that space.
One other additional point to that is the phase change is what we're looking for, vapor to water, right? So it's going to give up a lot of heat. It has to give up a lot of heat to condense into water. So if you take a 211 degree pot of water, right? You add 1 degree, it'll be 212. But to get it to actually turn into vapor, it's another 1,050 BTUs. So it's like way orders of magnitude greater energy to turn it from water into vapor, and then conversely to condense it back down. So like, even though there's a tiny bit, relatively speaking, of water vapor, the coil is having to work a lot harder to remove enough energy so that this will settle down and condense.
That's the same idea as if you put a pot of water, right, and you start to boil it, right? It's going to take temperature, it's going to take some time and some energy to get it from, let's say, 40 degrees up to 212. But then to get it to actually 212 to boil, it's going to sit there and simmer, and it's going to start to get those like little air bubbles in it, and then eventually it's going to boil. But it takes a while to do that. It takes a lot of energy. So it's sitting there and sitting in there and sitting there at 212, 212, 212, 212, 212, and then eventually starts to boil, and then we have the phase change. That phase change is right. It's about 1,000 BTUs. Yeah.
We have some clients, I think this project in particular had radiant heating, and they were interested in using their buffer tank as to connect to the ERV system as a post heater, post cooler. Obviously, they would need to insulate their ventilation ducts then, but just wanted to get your thoughts on that.
Yeah, so if you look at a traditional ERV, and let's say we're here in Boston, outdoor temperatures, let's say, is 12, 13 degrees or even colder, 5 degrees. The discharge air coming off of a high efficiency ERV is going to be somewhere in the 50 degree range, 50 to 55 degrees. So that 50 to 55 degree supply air coming off the ERV does need some post condition, because if you blew 50 degree air on somebody in the wintertime, it's going to feel really cold. So the idea of post treating it is a real thing. And so we either duct those ERV supply fresh airs into the return of a ducted system so it then can post treat it, or you can put a coil in, make that coil warm, and therefore that 55 degree air goes across a warm coil, 100 degrees or whatever, and comes out nice and warm on the discharge side, so it feels comfortable when it's blown back into the space. So it absolutely can be done, and it can be very easily done on an air to water heat pump. It'd be very hard to do that on a traditional refrigerant mini split VRF type system, but it can definitely be done. Yep.
The only thing I'd add to that is if you do that, you got to make sure you have a big coil, because you're gonna add static to your ERV, and they're not meant for it. So you've got to transition up to a larger coil so you have more surface area, less restriction to the coil.
That's right.
And then make sure you don't have like I saw one where somebody slapped a 1-inch filter in front of it because they thought they were going to protect it, and the static, the filter, the ERV moved like nothing for air.
Yeah, back to that like total external static pressure graph I was showing you. That each of those components matter. You got to get the size. You got to get its size right. Yeah.
You got to budget for your static. Don't blow it all on the smallest coil to save $100 on a coil.
So you sometimes do that? Do you sometimes do
We
buffer tank?
we do post treatment a lot if we're doing air to water for sure. Some projects we do electric resistance because it is a freezing concern, right? There is a chance that air coming off that core could be close to freezing, so we have to be concerned about that. In an air to water, it's going to be glycoled. It's going to be antifreeze anyway, so it's not a problem. But if you had like a traditional boiler system or something like that, I'd be worried about that coil freezing. So it'd be a concern there. So yeah, it depends on the project, but yeah, it can be done with air to water. Question in the back?
I love this old house I watched it all the time. I think it was your
Thanks
dad
for
who
watching.
was doing one recently, and he was talking about mini splits and mold.
Yeah.
So I was wondering if the new system that you're talking about, because it has the dehumidification, if it eliminates the need to like do that intensive cleaning scene with the mold, does it still mold up, or does it not really as much?
Well,
because of it?
yeah, so I mean, mold is just a microcosm of not providing enough dehumidification. So mini splits, like we were talking about before, have such high sensible heat ratios, they don't do a good job dehumidifying.
Right.
And so that's the problem. And so mini splits are getting misapplied, and the technology is going to the higher sensible heat ratios because that's how the rebates are incentivized. So you're going to have to put in ducted dehumidification with that style of unit. There's no way that I know how to make that system work with a traditional mini split.
System you were talking about is
Yeah, not a problem.
that doesn't have that.
Exactly. Yeah. Like we were talking about, we could do that chill water, we can reduce the airflow, we can play with all that to get the sensible heat ratios really low. Let that thing dehumidify like crazy. Just let the water come off that condensate coil all the time. Just let that water drain. Yep. Yep.
On the coils in the units versus.
I'm not sure the topic that or the segment that you watched, because we've done mold inside the building due to lack of dehumidification. We've also talked about mold inside the air handler cabinet. So I'm not sure.
It was inside the airhead thing.
Right.
But in the mini
On the
split, you have
coils.
a mold.
Yeah.
Because of the, where the coil and where the air is coming in with those mini splits.
Yeah, it's because the
And
coil's
the
on the cold, the fan's on the cold side of the coil, so when you when you do get the little dehumidification you get, you're tightening that air up, you're essentially squeezing, like a sponge. If I take a sponge and dunk it in water, when I take the sponge out, if I squeeze it, while I'm still squeezing it, it's still near, even though when I squeeze it, I'm removing water from the sponge, it's still right at the 100% saturation. It's not until I kind of let off that the sponge it's holding less humidity relative to what it can hold. And so because you have that moisture density, I mean, the air coming off of a coil, pick your coil, could be a mini split, could be a traditional air handler, whatever the case may be, right? The air coming off that coil is like 95% RH or higher, 98 sometimes. And so it's really moist, and then it goes right onto the fan motor, which is gonna collect moisture, it's gonna condense on that, and then add to it. Mini splits have lousy filtration, almost nothing, it's like a window screen. So you've got dust that moves through it, sticks to the moisture that's condensed on your fan.
That's right.
They just get nasty.
That's right. Yeah. Yeah, mini splits are notorious for they don't get maintained, the coils get dirty, they have no filtration on them, and then that's a perfect microcosm, right, of moisture and dirt billowing up, and then mold grows on that. You've had your hand for a while. Go ahead.
I'm sorry if I missed this part of the conversation. Is the ERV or the ERVs, I should say, for the space?
Potentially. We'll talk to the client about
Like,
that.
is the idea to have them independently ducted, or
Yes. Yes. Yep. We always try to have the ERVs independently ducted as much as possible. We try to have all ducted systems be independently done as much as possible. Doesn't always happen that way, but we try to keep things independent.
The reason I was asking, I was hoping you give the other answer, because I was wondering, we have a consultant who's like very adamant, like in let's say like a compact ducted air source heat pump system with dedicated exhaust in connection with the ERV. She's very adamant that the ERV be dumping on the supply, not the return side of the fresh air. And I'm just wondering I haven't got a chance to ask her, really.
Yeah.
But since you're an HVAC, I figured I'd ask.
Yeah, so
If you don't mind.
yeah, no. So if I have an ERV and I'm providing fresh air to the building, and let's say I'm going to try to go through the air handler ducted system, let's just say that's a decision we've made. I would almost always go to the return side of my air handler than the supply side. There's times we've gone to the supply side, but in most cases we've gone to the return side. The reason I like going to the return side in that example is because I get the post-treatment that we talked about before. So the idea is that I have a filter on that air handler. I have a heating and cooling coil. I have a blower motor. I can then redistribute all of that fresh air to all zones downstream, all spaces downstream, and I get the ability to post-filter it, post-heat it, or post-cool it, depending on the season.
Treatment. It's not just the raw.
Exactly.
Also just raw ERV air.
I mean, if it were on the supply side,
necessitates using the air handler too, the blower. You can't, because otherwise you're just dumping in the blower, and the return side is going to go out the return ducts.
That's right. That's right. Yeah, there are some situations where we dump it in the return, and once it's in the return, if the air handler fan is not operational, it's going to take the path of least resistance. So in some cases, it's going to go through the air handler. In some cases, it's going to go out through the return and dump it into space, right? So there are situations where we'll tie the air handler so they interlock together, and there's some times where we don't care. If it dumps it through the return, because the amount of time the air handler runs for heating and cooling most of the year, we're going to have pretty good run times. So exactly, yeah. So it may come out through the return for a small period of time, but then it's going to then turn on. It's going to then distribute through. So there are pros and cons to any decision. But if you're going to do it if you're going to tie them together, I generally would recommend tying it into the return.
Thank you.
Yep.
and then the pain in the ass passive house client says, oh, FIAS is going to make us claim fan energy for running the air handler all the time, or they won't give you credit for the distribution to the bedrooms. So then, okay, then our energy budget just ticked up.
Energy budget does go up. I will say the ECM motors are getting better and better and better over time. So if you have properly ducted, low static ECM motors, some of these are running at 50 watts. I mean, it's not nothing, but it's getting better. It used to be a huge fan penalty. Now it's still a fan penalty, but it's getting better. You had a question?
Your dehumidification system separate. Would you ever run it like parallel with the ERV so that it can suction the ERV?
We've done many jobs where we'll have a ventilated dehumidifier like a Santa Fe, and we'll take the ERV fresh air supply and dump it into the ventilation port on that ventilating dehumidifier. That works great. Because I get post-treatment, because they have MERV 13 filters on that, so I get the extra filtration level, I get the fan motor, and I get dehumidification. So I'm dehumidifying that air, I'm filtering that air, I'm getting post-treatment of that air before it comes into the system.
And then you have like a damper to send it that way or send it?
Well, yeah, I'll interlock it. So if the ERV's running, I'm going to leave that damper open. If the ERV shuts off, the damper closes.
Yep. The air system, do you find that there are any circumstances where they start being cost competitive with air-to-air, or are they still
No.
pretty much
No. No, it's a valid point. It's a valid point. I know Jason, some of the guys in the room are trying to change that, but if you just said, let's take 5 HVAC contractors and say, let's price out a Mitsubishi or LG VRF system, mini splits, whatever, and let's compare it to an air to water strategy, the costs will come back sometimes absurdly high for air to water. Part of it is because a lot of people just don't know about it. They're concerned. There's a fear there. They've never done it before. Let me just throw a high number at it. There's a lot of that going on. So that's changing, but that's still the reality right now across the industry.
Beyond the fear factor, though, if it were just equipment and like a knowledgeable contractor pricing it, does that change the answer appreciably, or is it just that the equipment and the piping is that much higher? We haven't hit the economies of scale from a buying perspective. Like when they order a shipping container or 5 shipping containers of Mitsubishi heat pumps coming over, that's hard for an air-to-water company to compete with that because they don't have the mass volume of sales like they do. So they might be getting a half shipping container even if it's the same technology and same product, inevitably there's going to be a lower cost from the manufacturer that's ordering 5 shipping containers versus half a shipping container or 10 at a time.
I actually have some numbers on that.
Yeah.
Spaceback, who's a fairly large air-to-water manufacturer, ships in a year the amount of air-to-water heat pumps that Carrier ships gas furnaces in a week.
Yeah.
So it's just the economy of scale.
It's crazy. Yeah.
Okay, so what does that mean?
I'm hoping that changes.
What does that mean in terms of price to the client then? I mean, because there are a lot of projects where, and I want to anticipate the things that we were talking about in the presentations about combining loads with domestic hot water, et cetera.
Yeah.
So, okay, we don't need a hybrid heat pump water heater, which is $2,300 or whatever.
Correct.
Does that start to offset the additional cost, or are we still?
Well, it depends on which HVAC contractor you're talking to. To be honest, I mean, if you're talking with someone that doesn't have experience with it or much training on it or much familiarity with it, there's no way that will be a cost competitive bid to a traditional means that they're used to, because their staff is trained on this. Yep. All they know is that, and that's what they do. But if you deal with certain other companies that have a different viewpoint on it, that start to get in hydronics and start to get in air to water, that will bring the price way down, but it's still going to be higher from my point of view. I don't know if Jason or if anyone else has any thoughts on that, but we still see air to water being a premium compared to a more traditional HVAC system.
How much of a premium? A lot.
But if you delete
Leave the concern about the fear factor and the inexperience. What approximately, given what you know today, what's the premium percentage?
Double, yeah.
Yeah, I would say anywhere from 50 to 100% on top.
Should be said this is all new construction or DER, right? We're not talking about the value of these air to water is existing conditions, right? So my house, my boiler just shut down, it was gas. I have a hydronic baseboard. So the cost to me is significant because I'm not talking about air handling, right? And so to be able to utilize an existing system could potentially be, that's where these things are starting to come in more valuable.
Yep. Yep.
You can't get up to the water temp of your existing radiators.
Yeah, no, I'm here.
Well, but if you improve your envelope.
The envelope.
Yeah, we need to do the envelope so you don't need the high temperature, so.
Yeah. Well, like, yeah, a little vermiculite, a little asbestos. No, but so if you have a traditional house in New England, right, that has baseboard heat or fin tube heat, a lot of those are designed for 160 to 180 degrees, right? So if you have 180 degree water temperatures, what's required to run through that fin tube to meet the heating load of that building, the problem is that air to water with current technology can only get up to maybe 140, right?
Is there a supplemental, use the existing,
Yeah.
What's over the coil?
No, so
removing heating systems means you're patching floors, you're doing all these things in remodeling.
Right.
Can you get 50%, 60% of the way there? And
yeah, so here's different options. So you could leave the baseboard in place, you could upgrade the envelope, obviously, and leave everything in place and go to air to water and get the temperatures low enough. That's one option. You could leave the building envelope as it is, which I wouldn't recommend, but you could do that, and you could upgrade to a larger radiator, right? That fin tube could become a panel radiator like they do in Europe, right?
Or could you do a preheat and then just boost it?
Then you can do a hybrid, right? So there's different flavors and different variations there. You could do a hybrid. We've done this many, many times where you have an air to water that covers you for the base load of that building. But when it gets down to 20 degrees, then you kick on the oil boiler for 20 degrees down from there. You know what I mean? And so, yeah. So you can do a hybrid as well. And I think the hybrid's going to be the way to go for most houses in a retrofit example in most cases moving forward. Yeah. Yeah, but that changes with R290. The CO2 heat pump can go up to 180. That can go to 176. I know a product right now that's CO2 refrigerant. It goes to 176 degrees Fahrenheit. What? Renew boiler? Oh, it is. It's R290. Yeah, not Eco. Or, hold on, it's Aerotherm. But it's going to be UK. It's Europe based. It's not in. It's not.
And Sanco can give you the high temperature, but it can't cool.
So right now the EPA regulation is that you can have R290 in a system if you have less than 150 grams of it. So if you have, what's that? I know, it's crazy, but that's the EPA limitation right now. So if you can get below that, we can make it work. Most of the 5-ton versions are going to be somewhere double or triple that in terms of refrigerant capacity. So we just need the EPA to shift that guideline up a little bit, and we're there. I know. So I'm wishing, hopefully wishing. Yeah, question.
Yeah. We talked a lot about load counts tonight. It's probably too late to start this conversation about HVAC grading and commissioning, but I want to just make sure that this crowd is aware of those, especially ResNet guidelines for HERS raters now requires HVAC grading. So all the work that gets done by Ross and folks like him on the front end, we HERS raters or a functional testing agent gets to come in at the end and make sure that the system is performing as designed, because obviously a lot of times it can be designed perfect, but it's only getting installed by humans.
Yep. So talk to the group a little bit more about that. You're saying HVAC grading. So are you guys providing a grade, like literally like a letter grade for?
Within your HERS rating now,
yeah.
There are various components. So we're comparing the design airflow to the tested airflow. So
yep.
If it's 400 CFM per ton and we're only getting 396, okay, that's grade 1. But if we're only getting 250 CFM out of the system,
right.
Now we might be grade 3. We've actually lost some HERS points, and the building is scoring worse.
Got it.
So you've got airflow. You can measure the refrigerant charge. You can look at several different items that are being measured on site.
Got it.
In person.
Got
Make
it.
sure the system is working as designed.
Okay. That's cool. I didn't know about that.
But a lot of this you have to do in conjunction with the HVAC contractor, because if you have like a mini split, you have to get the weigh-in number.
Correct.
And so
it's not just your HERS
It's a
rater.
big hurdle to get over.
Yeah.
I think at that point, we're gonna wrap it down. We might have to do like a after it's done, part 2 type of thing, like see what actually comes and what's installed.
We should do it. Yeah. Some monitoring. Yeah.
To be friendly neighbors. To be friendly neighbors, we're gonna wrap. Everybody's gotta be out of here about 8:30 or so. But that gives us 20 minutes to hang out, chat.
Okay. Cool.
Yeah.
Put your name in the bucket for the fine.
Oh yeah. That's right. Cool.